Hello everyone. It's Friday, July 25th, 2025. Welcome back to the channel. Today, I'm diving into a really cool trending article from the archives. It's one of those papers that just makes you go, "Huh? That's clever." Let's get right into it. The title is Accent Normalization Using Self-Supervised Discrete Tokens with Non-Parallel Data. The call is Schütze. Website 7.17,735. It's long. So what are we talking about here? Accent normalization. Basically, it's technology that can take someone's speech with a foreign accent and magically transform it to sound like a native speaker. But here's the cool part. Does this while keeping the original speaker's voice. So I could speak, and it would just remove my accent, not turn me into someone else. That's the dream, right? The big problem this paper is trying to solve is the data problem. To do this kind of magic trick, you usually need something called parallel data. That means you need tons of recordings of the same person, saying the exact same sentences, once with their foreign accent and once with a perfect native accent. Well, you can imagine. That's basically impossible to get in the real world. It's a huge bottleneck for this kind of research, so people have tried workarounds. One popular idea was to use a text-to-speech or system and take the accented speech. Use a speech recognition model to turn it into text, and they use a high-quality native-sounding text to generate an audio file. But oh, there's a catch. The voice from that system might sound a bit robotic, but the timing and rhythm might be a little off if you train your AI model to copy that. It can learn all these weird, unnatural habits. The quality of your training data limits the quality of your result. This is where this paper gets super interesting. They came up with a brilliant way to sidestep this whole problem. They call it using self-supervised discrete tokens. Okay, that sounds complicated, but the idea is actually very elegant. Instead of working with the raw audio, which is all the information about accent, pitch, and voice timbre mixed together, they first convert the speech into these things called discrete tokens. You can think of these tokens as a kind of simplified, universal phonetic alphabet. They mainly capture the content, the actual words and sounds being said, and they strip out a lot of the other stuff, like the speaker's unique voice. So their new pipeline looks like this. First, they take the original speech with the foreign accent. They also take that fake, generated native speech. They convert both of them into these discrete tokens using a model called HuBERT. Now the problem becomes much simpler. They don't need to convert complex audio anymore. They just need to train a model to map the sequence of accented tokens to the sequence of native tokens. It's like teaching it to translate from one phonetic dialect to another, because the tokens are mostly about content. It doesn't matter as much if the T voice was a bit fake. The model is just focused on laying the pronunciation patterns. For example, it lands at a certain token pattern and then uses it in English. Corresponds to a different, native-like token pattern. And then for the final step, they take this corrected, native sequence of tokens, and they use a second model, a synthesizer, to turn those tokens back into real speech. And here's the magic touch. They feed the synthesizer the original speaker's voice identity, so you end up with the corrected native pronunciation that's spoken in the original person's voice. It's a fantastic way to separate the problem into two manageable parts. But it's being said versus how it is being said. And they use some really modern tech for this, like flow matching for the synthesizer, which is a powerful new way to generate high-quality audio. One of the most practical things they tackle is duration control. This is super important for things like dubbing. If you're replacing dialogue in a movie, the new speech has to fit the actor's mouth movements perfectly. The timing has to be exact. They explored two methods for this. The first is a simply scaling approach. It just takes the generated speech and stretches or swishes it to match the length of the original. It's a bit brute force, but it works. The second method is much smarter. It's a flow-mating-based duration predictor. that is aware of the total duration from the start. Tries to generate speech that naturally has the correct length, which results in a more natural rhythm. It's pretty amazing stuff. So, how well did it actually work? The results are pretty impressive. In their tests, their proposed system beat the more traditional frame to flame method, naturally missing speaker similarity. People who listened to the samples thought it sounded better and more like the original speaker. It also did a much better job at actually reducing the accent. And they showed this with a really cool chart, which visualizes the phoneme distributions. Before the conversion, you can see all these hotspots, where the accented pronunciation diverges from the native one. After the model does its thing, the chart cools down, showing the pronunciation is much closer to the native target, but they're also very honest about the limitations. The word error rate or word was still a bit high. This means that sometimes in the process of changing the accent, the speech can become a little less clear, and an automatic speech recognition system might misunderstand some words. So, there's still a trade-off between accent and clarity. Now I think my favorite part. How could we use this in real life? The applications are just so cool to think about. First, language learning. This is a huge one. Imagine an app where, as a language learner, you can say a sentence in your own accent. The app would then play it back to you instantly, but with a perfect native accent in your own voice. You could hear exactly what you need to change. It would be like having a personal pronunciation coach available 24/7. Second, the entertainment industry, especially movie and dubbing. This could be a game changer. Instead of hiring a whole new set of voice actors for each language, you could potentially use this technology to take the original actor's performance, with all its emotion and nuance, and just convert the accent to be native for the target audience. The duration control feature is absolutely critical for this, to make sure the new dialogue syncs with the video. And third, accessibility and communication needs. Who might struggle to be understood by voice assistants like Siri or Alexa, or even by people on a phone call. This technology could act as a real-time filter. It would convert their speech into a more standard accent on the fly, making communication smoother for everyone, without erasing the person's vocal identity. It really empowers the speaker. So to wrap it up, this paper is a fantastic example of clever problem solving. The key insight of using discrete tokens to separate pronunciation from voice identity is just brilliant. It neatly sidesteps the huge problem of needing perfect parallel data. While there are still challenges, but this token-based approach feels like a major step forward. It really opens the door to so many exciting possibilities. Alright, that's all for today's dive into the archives. Super fascinating stuff. Let me know what you think in the comments below. See you next time.